All right. Good day, everyone, and welcome to this session, the Science live stream session here. Hey, my name is Nik Alleyne, and I'm standing in today for Dave Halser. Now, I know this is some big shoes for me to fill, and I know that Dave typically likes speaking, at least these days, about the machine learning, the SEC 595 class, as well as the SEC 503 class, the intrusion detection in depth. So continuing along Dave's team, I am going to spend some time today talking about machine learning, as well as we will look at this from a practical perspective where we will actually write some code. So the objective, basically, we are going to use machine learning to reduce the alert fatigue. And why is this important? Well, before we get there, just some quick notes about me. I'm currently a director of business development at a managed security services provider, and I teach the SANS SEC 503, which is the intrusion detection in depth class, as well as the SEC 504, which is the hacker tools, techniques, incident handling class. I also blog at securitynick.com, so feel free to come hang out there with me sometime or check out my blog, as well as I'm the author of these two books, Mastering TShark Network Forensics and Hack and Detect. Welcome, David. Now, before we go any further, it's important that we understand the views here are basically my own. Welcome, Ali from Germany. The views here are my own. They are not reflective of my employer, nor are they reflective of SANS. You're basically my own. So the problem is we have a situation whereby, there are a large number of security tools on the market, and a lot of these tools generate some type of alerts. And the more tools we have, the more alerts we get generated, the more we have a problem in terms of the number of the alerts we have to process, which contributes to the alert fatigue. Now, there are many different ways to solve this problem. We are just looking at one possible solution today. For example, if you are writing rules, you might want to, or if you're developing specific use cases, you might want to ensure those use cases are targeted to your particular problem or to your particular signature. Same time, you can probably ensure those rules are effectively tuned. But for today, we'll just look at using machine learning as a solution to this problem. Thanks, Emery. Much appreciate that. Welcome, Ankur. So here's a topology that you should keep in mind. So for us, let's say we have a situation where, and in this example, I'm using the SIEM, but this can be any security tool that is generating an alert. And we have a SOAR, Security Orchestration, Automation, and Response tool. What is going to happen is the SOAR picks up the alerts or the offenses or the messages and notables, whatever it is you want to call them. The SOAR picks up these alerts from your security tool, stores some information locally, and goes out to your threat intelligence provider, for example, enriches that content, and then ultimately goes to your case management solution. Whatever that incident management solution is, your choice. But ultimately in here, we will classify the data. The data will be classified as to whether it is a true positive, it's a false positive, it's benign, it is a non-issue, whatever it is. Ultimately, this classification is what allows us to be able to develop a machine learning model that we can then feed back into the SOAR. So when it receives an offense from here or an alert from here, it can ultimately make a prediction as it creates the ticket here as to whether or not this is a likely true or false positive. So this is what we're trying to do today. We want to use machine learning in conjunction with our SOAR tool or any other tool to be able to predict when a ticket is being created, whether or not that ticket is more than likely a true or a false positive. And do note, I said more than likely, but we are not going to look at the probability side of it in terms of checking whether it is 0 or 0.5 or 0.7 or 1. We are just going to make a decision it is true or false positive. So we are dealing with a supervised machine learning problem here. Now, this is going to be practical, hands-on. We're going to code. But if you really want to get more deep into this, you can definitely check out the SANS SEC 595 class, which is the Applied Data Science and Machine Learning class for cybersecurity professionals. If you are interested in packet analysis, check out the SEC 503 class, where we talk about intrusion detection in depth. And on day 5 of that class, we go through machine learning also. So with that said, and we have set the stage, let's go ahead and write some code. Question is, will the deck be shared at the end? Probably will, but there's not much in the deck. Honestly, there's not much in the deck. This is more of a practical session we're having. We're going to write the code. We're going to analyze it. We look at machine learning from the machine learning pipeline. All right. With that in place, let's go ahead and write some code. In my case, I am going to use Visual Studio, Visual Studio Code, or Visual Code, if you want to call it, VS Code, right? And we're going to write some code in here to address our machine learning problem. So first up, we need to import some libraries. And let me see. If this screen is too small, please let me know. Let me see if I can maybe increase the font a little bit. Let's say font. Let's make this 20. Let's see if it makes a difference. Okay, this should be a lot better. You should be able to see the code clearly there. Okay. So first up, we are importing pandas, right? I'll import it as PD because this is typically what we do as standard. And then at the same time, I'll import NumPy as NP. These are the first two libraries that we are importing. Now, if we are going to do anything with machine learning, we have to gain access to the data, because we should know that in machine learning, the data is what is king, queen, prince, princess, whatever you want to call it. So the data is the boss. And now that we have pandas, let's go ahead and say we're going to use Panda, and we're going to read a CSV file. Okay, where is that file? Well, let's read that file as a raw string. And the file in my case is located on my D drive in a folder called ML, and it's the file name security incidents.csv. Now, this file is a CSV file, and CSV files typically have a header. So for me, the header is in the first record, which is at position 0, or the first row. Similarly, we just mentioned that this is a CSV file. So we know CSV stands for comma separated values. So let's say that the separator here is actually the comma. We're just enforcing it there. Now, what you might notice sometimes also when you import data with pandas is, what you might notice is that sometimes when you import, you get encoding errors. So for us, let's just say encoding errors equal ignore. So we'll ignore that. Welcome, Michael from Louisville. And for us, let's just take a look at the first 5 records just to see what this looks like. Good. So here now we have read our data set, basically the first 5 records, but we have not really assigned this to a variable. We need to assign this to a variable so that we can reuse this content later on, right? This data. So let's go ahead now and change this. Let's add, we can call this any variable. I'll call it data frame, as in the DF. I'll call it security underscore incidents. Because remember, everything we're dealing with here today represents security incidents generated by your security tool that ultimately resulted in a ticket in your case management system. So now that we have this here, I will remove head so that we can get the entire data set. And at the bottom here, I will take advantage of the security incidents. Once again, I will use head, look at the first 5 records, and we're good. Now, the first part of machine learning is once you have access to your data, you are supposed to spend some time exploring that data, understanding what your data consists of. So for us, the first thing we will do is look at the info from the data frame. So I'll say DF, security incidents, and I'll say info. And here now, we see we have a pandas data frame. We have 27,001 records that are numbered from 0 to 27,000, which we see here now. We have 3 columns. We have column 0 represents description. Column 1 represents detail. Column 2 represents status. This is exactly what we have here. Description, description, details, details, status, the status. Welcome, Sarah from Ireland. These 3 columns here This one and this one represents our features. This one represents our label. The labels that we're dealing with are, at this time, true positive benign and false positive. These are what we're seeing. But are there other labels? I mean, in the end, we want to have a binary classification problem whereby we're predicting, is this a true or a false positive alert? So for us now, let's take a closer look at some of the incidents before we actually come back to this column here, right? This is our target. This is what we want to predict. This is feature 1. This is feature 2. What we ultimately are going to do is we're going to take this feature and combine it with this feature via feature engineering, and we'll create a new feature that we'll probably call data or something. Let's take a look at the first record here. So to do that, I will come in this cell and I will say now, we'll access the data frame again, right? And specifically, I'll access the description field. Okay, I'll just copy it. Yes, there. And in this case, just show me the first record. We don't need to look at all of them. We just want to get an insight into what these different fields contains. We can look at the top here, and we already know some of these values. We can see all of them basically represent text. But let's just take a closer look at the first one from the description perspective. We can see this is what it looks like, right? We can do the same thing from the details perspective. And let's do it slightly different this time around also. Let's say we take the DF security incident, which is the data frame. And in this case, we look at the details field. Note in this example above, I accessed it in this way versus now I'm accessing it via like a subfield, if you wish. And still just showed me the first entry. So we have the description, right? And we have the details. What we ultimately are going to do, we are going to combine these two and create a brand new feature. And that feature is what we are going to use as our data to train the model. Now let's take a look at that third field. Remember above here, right? Above here, we have the status. And the status we can see currently, it says true positive benign. We see false positive. But is there anything else that we should be aware of? Let's see. Scroll down back here again, and let's go once again, access the data frame. Okay, we'll access the data frame again. We say DF security incidents, and we're going to access the status field. And now that we have this field, let's get a value, but in getting the values, let's get counts of the values in also. Now we see that that field, the status field, actually consists of 3 different labels. Okay, we have a false positive, we have a true positive benign, and true positive malicious. Ultimately, we will want to consolidate these two to make it just true positive and false positive. Remember, just for context, if you're joining us late, we are looking at taking the tickets. So your security tool generated an alert. You created a ticket within your ticketing system. You then ultimately, after analyzing that ticket, classified it as a true positive or a false positive. And we ultimately want to get to that stage where we have a false positive or a true positive from our prediction. But right now, we have 3 classes. We need to consolidate this to 2. Thanks, LinkedIn user, on the nice trick there. Yeah, so we need to now consolidate this down, consolidate these 3 classes here, right? These 3 classes to 2. Okay? Now, in some cases, some folks are okay with seeing these numbers the way they are, but not everyone is like that. Some people are more visual. So let's say from matplotlib, let's import pyplot as PLT. With this, we are now going to graph these values so we can get a better understanding of what is going on. Okay. First up, let's say as we create that chart, or as we create our chart, let's give it a title, and we'll call it status distribution. Okay. Along with that, let's plot a bar chart. And in plotting this bar chart, let's say on the x-axis, we will put from the data frame, we will put the status, right? Remember the status column, okay? And we will look for the unique values there. And on the y-axis, we'll call that height, right? We'll we'll use the DF security incidents once again, the same data frame, but this time we're going to look at the status again, but at the value counts. Okay, at the value counts. We'll say, okay, we'll color this as red. We will align, let's say center, right? Let me just wrap this here so that you can see what is going on. Wrap, okay. I press enter here. Let's say we, on the X label at the bottom, or on the X axis if you wish, let's say we call this labels. It says, someone says it misspelled title. Oh, T-I-T-L-E, thanks. Thanks. Okay. Status distro won't print, Nick. You missed it. Okay, thanks. I saw it. Thanks. Appreciate it. Okay, so we have the X label, and let's plot the Y label, right? Or let's label that, I should say. Let's call that count. And for us, let's just say X ticks. Let's set a rotation of 45 degrees so that the strings at the bottom that represents the label can be clearly seen. So if we did this correctly, we press enter, we can see here now we have a more visual representation. But if you look here, you are seeing true positive benign being reported as the most, when in fact, based on what we saw above, and let me come here, based on what we saw above, false positive should be the most. So what really transpired here? Well, it has to do with the ordering. Yes, the question currently is there going to be a recording for this? Yes, you will be able to access this session directly after we finish here. Okay, you will be able to access the session directly. All right. So now this here does not look to be what we wanted it to be, because we know that true positive benign is not the most. Actually, true positive benign is the second most. The least is malicious. So we need to fix this here. So what we will do, we will say, okay, you know what? I need you to sort this here. Now that we run this, we see we have false positive as the most. This is exactly what we expect, right? We have false positive as the most, true positive benign next, and now we have the malicious as the least. We're now making progress. Exploring our data and understanding what is here is extremely important for us, okay? Remember, we are trying to solve a classification problem. So we have this here as false positive, but we have these two as true positives. So what we can do here is we can combine these two and make it into one. Let's go ahead and do that. So we come down here and we say, just for simplicity, let's just say, you know what, it's okay. Let me just do this here. So what we will do, we'll say, we'll take the DF security incidents, right? We'll take the description field. DESCRIP. Okay, description field. And we will add it to the DF security incident field details so that we can combine the two. What we will recognize here is that once we put this plus, yes, we are joining the two fields, but at the same time, the two strings, the one that ends one section and the one that starts another one, are going to be joined together. We don't want that. So let's instead say we put this way and we put a space between these two. So now when we look at this, we have just combined the two fields, but we need to get this as part of the data frame. So let's go back now and say, on the data frame, security incidents, right? We want to create a new field, and we'll call that field data. Now that we have this field here, right, that consists of the description as well as the details, let's go ahead and look at the security incidents data frame again. And this time, as we did before, let's look at head with the first 5 records. Now we have added the new column, basically consisting of the description as well as the details. So we just engineered a new feature. Okay, so we have this here. So we are making progress. Now we have another problem. Let's stick right here for a second, right? Right now, this label says true positive benign and true positive malicious. What we want to ultimately do is get this into a numerical format rather than the categorical values that we have here. We want this into numerical. So we wanted to say 1 for true positive and 0 for false positive. 1 for true positive, right? As in, this alert is a cause for concern in my environment. I should go investigate this deeper because it is more than likely my organization has been breached. So we want 1 for true positive and 0 for false negative, or false positive, I should say. Sorry, not false negative. So with that said, let's come back here now and let's say, you know what? We are going to take the security incidents, right? The subfield, which is status. And we are going to say, we are going to map this. And in mapping, we're going to create a dictionary. Okay? And for this dictionary, let me create some space here. We'll say that anywhere, let me just copy these here, just for simplicity once again. Copy these here. Right, and let me just create some space here. Okay, we'll say any place where we see false positive, right? We put this in here. We are going to take that and put it as 0. Similarly, any place where we see true positive benign, we are going to make that into a 1. Once again, similarly, any place where we see true positive malicious, we are going to make that as a 1. Right? Because it's true positive. So we're going to consolidate everything that is true positive and just keep it that way. Now with this in place, let's go ahead and add yet another field. So we'll call this one BF security incidents, and this field we will name, sign it to here. This field we will name, let's call it Y labels, because this is ultimately what we will use as our label in our model. We wrap here again, right? And with this said, let's go ahead once again visualizing what our new data frame look like with this new field. Syntax error, dictionary. So here should be closing here. Question: why not make benign 0.7? Because we're looking for a classification problem. We want either 0 or 1, right? We're looking for a classification problem. Let me just see what is going on here. Let's map here. Let's make this into a dictionary. And here, oh, I see what my problem was. If it's a dictionary, we need to put it in here. Sorry about that. Let me just cut out here. Sorry about that. Oversight on my part. This is what happens when you're doing things live. Now, for the LinkedIn user that asks why not make true benign 0.7, we can, if we want to have a multi-class problem, right? We can. In this case, I'm just doing a binary classification problem, right? So it's either true or false, yes or no. But we can, if we wish, change it to something else. Okay. So now with this, let me in here look at the head 5, right? So we have now created a new label which says Y, or a new column which says Y label. And for simplicity, considering above here, we already plotted this and we had 3 different categories. Let's now plot this new column that we created here to see how many categories we have. We should only have 2, which represents basically 0 or 1. So we'll take the data frame, and rather than using matplotlib or Seaborn, as we will touch on shortly, we've used matplotlib already. Let's now instead use pandas plot functionality. So we'll say on the Y labels, we want to look at the value counts as we did before, and we want to plot a bar graph. Okay? Now that we plot this here, we see we have 2 categories. This is exactly what we want, right? We have 2 classes. We have class 0, and class 1. So this is exactly what we want and where we want to be. So we have consolidated our labels so far. If we look at the shape of this data set, right, we can see we have 27,001 records with 5 columns. This is 27,001 samples, or you might call them example, but 27,001 rows, right? Each one of them representing a new alert, and 1, 2, 3, 4, 5 columns. So this is why we have a shape of 27,001, 5, because we have 27,001 rows and 5 columns. We don't need all 5 of the columns, but we will get rid of those shortly. Now, let's visualize this once again to get a better understanding of the proportion of these zeros and ones. So if I take this security incidents again, and note, most of the time with your machine learning, you will spend doing exactly what we're doing here, understanding the data before you actually attempt to build a model. So here we have the security incidents once again, and what we're going to do, we're going to look in to the labels. We'll get the value counts, right? And we have those values once again. Now we have this here for zeros and this here for ones. Remember, the ones have now been consolidated. But what is the percentage of this distribution? Let's run here. Let's say we take this same value counts. Let me copy here. Right? And instead, let's access this row, which would be represented by 1. Not 1 because of the fact that it's labeled 1, but 1 because this is where it is in the array, right? This is the position in the array. So this would be position 0 in the array. This would be position 1 in the array. So we're accessing that, and we are going to divide this by, let's take the shape here, right? We'll take the shape, and from the shape, we will extract this field that represents the total amount of records we have, okay? So we'll just say here, we'll access field 0. Now, we press enter, we can see we have 0.15, which would suggest 15%. But let's just, for the sake of our own sanity, confirm this. So I will say round, and when I round this, I will round this off to 2, and I will multiply it by 100. So there we go. We have 15%, which means this here represents 15% of the total security alerts that were generated or the tickets that were created. Okay, so here, as you look at this, keep in mind, if this is 15% here, this is 85% here, which means this ratio is significantly large. You probably have maybe about a 5.6 to 1 or something like that ratio. Keep that in mind as we go through the rest of the session. Now, I already said that, we have all of this data up here, but we don't really need all of this now. We constructed new fields for the labels as well as the data. So we are going to drop description, details, and status so that we can only focus on these two, which is what we're going to use as our input. We will have the Y labels as the labeled data. And here the data, well, this is going to be our features that we are going to submit. So to drop those columns, we will take advantage of pandas once again. I will say pandas, let's say DF security incidents, as in the data frame. We want to drop. What do we want to drop? We want to drop specific columns. And we will take advantage of this via an array. We'll say we want to drop the description column, followed by the details column, followed by the status column, right? And because we don't want to make a copy of this data frame, we will say in place equal true. So we're doing this with the live data frame. You might not want to do this in your environment, but for what we're doing here right now, this is how we're taking it, or we're getting it done. Now let's look again at the data frame with the first 5 records. Press enter. Now we can see that whereas above we had 5 columns, now we only have 2, which means if we look at our shape again, we see we have the same 27,001 records, but now we have only 2 columns. So this here, data, as well as the labels, these are the things we are ultimately going to be using to train our model. Now that we have the data ready, in machine learning, you typically want to have 2 or 3 sets of data. You will have your training set, you will have a validation set, and you will have a test set. For our purposes, we will stick with 2 sets. We'll have the training set and the test set. To help us split the data, we can use tools such as, let's say, from sklearn, model selection, sklearn import train test split. We can actually use Python slicing, and we could slice this data set ourselves manually, but let's take advantage of the built-in libraries that are there to help aid this process. So now that we've activated this train test split, let's go ahead and split the data up. So we'll say we want X train, right? This is going to be used for training. We say X test is going to be used for testing. Similarly, we need the Y train as well as the Y test. We call the train test split function, and we'll say we want to use the security incidents data column as the X side of it, and our labels will be found in the DF security incidents Y labels. At this point, thanks LinkedIn user, much appreciated. At this point, let's go ahead and also set a random state as 10. Doesn't have to be specifically 10. The idea is that I want to ensure that anytime I repeat this experiment, I must get the same results. So with that also, let's add one more thing. Let me wrap this here. We'll say we want to stratify, right? Stratify. And we will take this field here for our stratification, if you wish to call it that. What am I doing here? The idea is, if we look back at the top, right, we know that the proportion of 1 to 0s is not the same. Okay? There's a question on if the wouldn't my prediction be much better if I use all of the columns? Actually, no, it wouldn't be much different, because remember, in this case, I took the description as well as the details and I combined together. I could use them separately, but it's the same data that I'm basically using. We can create additional features, but in this case, and let's be clear, it's not necessarily that the more features you have, the better your model will perform. So for this problem I'm attempting to solve, I am just using the description and the details, and I combine them to create a new feature, which is the data. Okay. So I was saying also that if we look here, we have this large number of zeros versus the ones. So if we split the data, we can have a situation where we have all zeros or all ones in maybe the train or the test set. You don't want that. So we want a similar proportion of the ones and zeros across the test and the train. So this is why I am stratifying it. Okay. If this goes according to plan, it looks like we've done this well. We've got no errors. Let's go ahead and test the shape now of all of these different sets here. Let me just copy here and I'll paste here and I'll just say, give me the shape. I'll just copy and paste for simplicity. Simplicity. And when I get the shape, we can see now that at this point here, we have 20,000 records in the X train. We have 6,075 in the X test. Oh, you know what? Let me do something else. I just recognized something. What I should have done, I should have also specified how I would like to split this data. It looks like the system probably split it by default in an 80-20 ratio. I instead want to split it on a 70-30. So I will say train size is equal to 0.7. And if my train size is 0.7, it automatically means that my test size is 0.3. So now I run this again. And now we have another set of values, right? So I dictated here how I want my train and test set to be split. So with this in place, let's go ahead now and take a look at one record from the training set. Okay, so I will just say X train. I will say, show me the first record, 0. And this is what it looks like. So this is the combined data. Now that we've consolidated everything around our training set, let's once again now visualize this data a little bit more. Because once again, I know you might be thinking, we have not really done any quote unquote machine learning as yet. But most of the machine learning work is actually done at the beginning with what we're doing here. All of this exploratory work, all of this analysis and so on that we're doing, setting up features and all of that. This is where the work is really done. Before you will see writing the code to build a model is not going to really take much. Since we are still exploring, let's use word cloud. Let's say from word cloud, import word cloud. This is going to allow us to visualize the content in here so we understand how things are used, because we don't want to keep content that is used or words that are used heavily. We ultimately want to focus on things of interest. So I will say my word cloud, this is just a variable. right, is equal to, let's say, word cloud, and I'll say max font size. Let's say that is 50. Let's say with the maximum number of words we want in here, let's call this 100. Let's say the background is white. And let's use this here now to generate on xtrain 0. Right? Let's at the same time say, you know what, let's plot a figure, and let's say the figure size is 10 by 10. And let's wrap this up by simply showing our word cloud. Okay, so there we go now. We have a better visual of what is going on here. Now, for some of us, keeping words like alert might not be valid, right? Because you don't, not because you have all of these words, that means you must use all of these words. We ultimately want to consolidate this as much as possible, remove unnecessary words. So timestamp might not matter to me. The string username might not matter, but the actual username might be of importance. Similarly, time might not be important. Category might not be of importance, but the actual category that this belongs to might be important. So you will have to make decisions on which text you keep and which ones you discard. The ones that you want to keep, ultimately, the ones that you want to discard, you can use those as your stop words. But for the ones you want to keep, then those are what we're going to use to build our model. Now, let's take a look at this from a different perspective. Let's say we decide, you know what, let's set up a variable called all words. Right, and we say xtrain. Remember, this is our training set we're working on. Thanks, David. Much appreciated. Yeah, we want to influence the words that are we want to influence the model by choosing words that are meaningful. So we say xtrain here, and I will convert this to a string, right? Remember our training data, right? And I will say, want to split this here by the space. And once we split it, give me the values and convert these values to a list. If I now look at all words, right, and I look at, let's say, first dimension, let's say the first two records. Let's say the first two records, right? I press enter. We see here now we have a situation where we have what seems to be a list of lists. So we ultimately have to flatten this here now, right? We have to flatten this because we want to get one flat list. Let's go ahead and now say, hey, you know what? Let's use Python list comprehension. And let's say we want to create a new variable called flatten words. And this is equal to, let's say we say for word in all words. Remember, all words is the variable we just created. What we could have done, we can say for word in all words, just print word, for example. But that's not what we want. Okay, we want to go a little deeper because we want to flatten this array. So I will remove this here and I will instead create another for loop. So I'll say, no, for word in all words, then we say for new word in word, then print the new word for me. Right, and this now is going to be seen as one Python list that we have just flattened. So I'll say flatten words and show me the first 10 records. Right, boom. Now we have flattened this. Above here, we had basically like a two-dimension array, if you wish, or a list of lists. Here, we have now flattened this list, which allows us to look into here and get a little bit more visibility, once again, on the usage of the data, right, of the text. So let's now import, let's say from collections, import counter. Okay. And now that we have imported counter, let's say word counter, right? This is just a variable. We say counter. We want to run that on the flatten words. And now that we have that, let's look for the most common words. This is just a variable here, but I'm calling the word counter most common method here. And once we have that, let's look for the most common words, top 10. We press enter. And here we can see the frequency and the usage of these words. Once again, you have to decide, do I want to keep the word IP? Probably not. You might instead want to use the IP address. So you might decide you want to drop these here because they might not be meaningful to what you're doing. Let's take one final look. Let's say we created, and this is where we're visualizing again. Let's say we create a list. Let's say we create a list called X words. We create another one called Y conks. Right? We call this two lists here. And in these lists, we're going to say for word and count in most common words, which is exactly what we have here, right? This value here. We're going to take those words. Let's say we take the first 25 of them. Okay? We're going to say X words. We want to append, right? Add the value, which is the word. We want to take these words here and append them to here. Similarly, we'll do the same thing. We'll do the same thing for the conks. We'll say Y conks. I want to append count, which is these values here. Okay, let's go ahead, run this. We have not received any errors. So now let's import yet another library. We don't have to. We can use matplotlib or something else, but we're doing things differently for you to see different perspectives. So I'll say import Seaborn as SNS. And with Seaborn imported, let's go ahead and plot these texts that we just created there, or these texts here and the values that we've appended to these two lists. So I'll say, let's say plot that figure. Let's set up the figure. And we'll say the figure size is equal to, let's say 5 columns, 10 rows. At the same time, let's plot on the X label. Let's call these here conks. And plot on the Y label, we'll call these, let's call them unigrams because we're looking at individual words. And now let's plot a bar plot. Plot a bar plot. We say on the X-axis, we want the conks. And on the Y-axis, we need the words. And let's remove, or let's despine it so that we can remove any square brackets, the square lines that would come with the image. So let's say SNS.despine. Okay. We did this correctly. We press enter. We now see we have yet a better view of how our text is distributed, which means once again, you at this point have to decide whether or not you want to keep some of these words, but at least you have visual of what is going on. And as we talk about keeping some of these words, let's jump right away into the stop words now. So I will set up something here called my stop words. Right? I'll call this, I'll set up a list. And in here, if there are words that I think are not meaningful to my analysis, I will add them. Right? If I think these words are in no way going to help the algorithm, it's going to add additional noise, I will add these. So I'll say, right? And I'll just leave it here. Let's just add a couple more. Start. You can add whatever you want. Do keep in mind that you can use the default stop words, but if you understand the domain that you're trying to solve this problem for, that is going to significantly influence whether or not you use the default stop words. Let's continue. Let's say now we want to set up a tokenizer because we need to split all of the sentences into individual words. And we'll say here, let's say regex tokenizer. This is a variable, okay? And I will say we'll use the NLTK tokenize NLTK. Okay, I think I might have missed something there. I think I needed to install NLTK. Let me just see something here. All right, NLTK. Let's see. Did I import it? Let's come here. Let's see. Okay. So now that we have import NLTK, we should now be able to take advantage of that library. Okay. Now let's do one more thing. Let's just say, because I think it's going to complain here also. Let's say NLTK dot-download. Let's say we want to take advantage of prompt. Okay, good. That's in place now. Now let's go back to where we were before. We probably got a little bit ahead of ourselves there a few minutes ago, but that's fine. All within the part of coding live. All right. So we say NLT. Yeah, thanks, Jincy. Much appreciated. So we say NLTK dot tokenize, right? And we say we want to use a regex tokenizer. And we're going to split on the space, right? And we'll say gaps equal true. At the same time, we're going to set up a stemmer. Let's say PS, as in porter stemmer. We'll say PS stemmer. Is equal to NLTK dot port stemmer porter porter stemmer. Okay, we leave this here. Now, with all of what we've done before already, we still have to quote unquote clean this data. So to clean this data, let's set up a function. Let's call it clean data. And why a function? Because ultimately we will have to, the same task that we perform on the training data, we will have to perform on the testing data. So if we have a function that we can just apply, then that makes things a lot easier. For now, I will just say print. I will just say cleaning the data. Right? On that. And at the bottom now, we'll say xtrain, right, is equal to clean data, and we'll give it the xtrain here. Now, all it says is cleaning data because we have not really done anything meaningful. So let's go ahead and get some real work done. Let's say first up, we'll say we want to create cleaned data, right? And clean data is going to be, we'll take the data that is coming in as input, right? In this example below here, it is the xtrain data, but whatever that data is, we'll take that as input. We'll convert it to a string, and then we'll make it lowercase. Why? Because uppercase SANS and lowercase SANS is going to be viewed differently by the model. Similarly, if we look at the data above here, if we look at the data here, we see we have things like this square bracket. We see we have the new line character. We probably have tabs and all of those things. We want to remove some of those, if not all of them, I should say. So with that, let's go ahead and continue cleaning the data. So we'll say now, this cleaned data again is now equal to cleaned data as string, right? We will replace clean, instead make this cleaned. C-L-E-A-N. Okay. Say cleaned data that string, and let's say replace. Let's hope we're getting this right. String replace. And we'll say we want to replace wherever you see a /n, just replace it with a space, right? Similarly, we can add on here, we can say string.replace, and we can say wherever you see the /t, we replace that, right? Let me just copy and paste here for simplicity. Let's hope in copy and pasting I don't make a mistake. Let's say wherever we see this bracket, and wherever we see this bracket here, we need to come back in here. Let's replace these here with space, replace with space. Okay, we got that right. We're writing a lot of code here without testing each line, so work with me. Okay, let's say also we have 10 minutes to go. Okay, let's see. We more than likely are going to go slightly over the 1 hour, but please work with me, right? So we say cleaned data, and we say cleaned data, and we are going to apply lambda to this here. Okay, we say x is going to be our input. And we will say we want to take advantage of Python list comprehension again. Since I explained the first one, I'm not really going to elaborate much on this one. But what we want to do, we want to say for word in X, which is the input, if word not in my stop words, remember we defined our stop words above, then ultimately keep that word. Okay? Now, I will also decide that I want to join those words. All right, so I'll close off here. Close off here. And in joining it, I will say put a space between. Okay, and let's do one more before we close up here on this cleaning. There's a lot more cleaning we should be doing, but in the interest of time, let's just do one more. Let's lemmatize it. Lemmatizing is whereby, we have, let's say, testing, tested, testing, tested, test. All of those have the base word of test. So we want to just consolidate all of those to one word. So we'll say cleaned data is equal to cleaned data. We'll apply a lambda once again, X. And here we'll say for word in regex tokenizer, tokenize X, which is our input, we are going to run the PS stemmer that we created. We're going to stem those words, right? We'll say word, and we'll say to lowercase. We did lowercase above, but I'm just saying do it back here just in case we missed anything. Now, if everything went according to plan and we have our function in place, then let's go ahead and return the cleaned data. Okay, let's press enter. Looks like everything went good there. Let's say, let me do one more thing here. Let's just say print finish cleaning. Okay, we run this, cleaning the data, we got an error. Object has no attribute string. Where is that? Data, clean data extrain. Let me see if I say as type. What did we miss? Okay. Rahul, we were going so good all the time. Where did we miss something? We say extrain. Okay, let me see here. You take the data as input, clean the data, extrain, object. Give me 1 second. Let me see if I can figure out what we did wrong here. Alert. Did we do anything else with extrain above that would influence that? Okay, I accidentally reassigned the extrain when I did just a print statement in the function. Accidentally reassigned it. Where did I accidentally reassign it? Accidentally reassign extrain when you did just the print statement. Oh, okay, it's quite possible. Okay, I get what you're saying. So this is the thing also. So what we want to probably do here is, let's come back here and run this here. Let's, from the split, right? We run it, run here, run here, run here, run here, let's run here, run here, let's run here again. Let's see if we get this right. See? Looks much better. All right, so we're cleaning the data. We're in a much, much better position. Thanks, Philip. Greatly appreciated. All right, let's go ahead now and in the interest of time, start preparing to close this up. Okay, now there are other things that we can do. Thanks, Daniela. There are other things that we can do here, but we're finished cleaning. But in the interest of time, let's just prepare to wrap up and actually build the model, right? Now, we know that when we, for example, did extrain, right, 0, we know that we have, oh, maybe I missed something in here, but anyhow, we know that it's text that we are feeding to this model. What we need to ultimately do is feed this model numbers, something numeric. So how do we get this number? How do we get the text into numbers? How do we get the text into numbers? There are a number of different approaches for this. We can count the frequency of the words. We can give each word an integer value. For us, we will use something called term frequency, inverse document frequency. So to help you understand what that is, let's go ahead and import SK from sklearn. sklearn.feature extraction text. Import TF-IDF vectorizer. Now, what is going to happen is, let's say we have a couple of different documents. Okay, let's say we call it a corpus, and this corpus consists of 3 documents. Let's say the first one is SANS rock. The second one consists of SANS rock paper. The third one consists of SANS rock paper scissors. What will happen is, this here, when it converts to number, because this is the first document that it's seen in, it's going to have a high weight. Now, once we get to the second document, SANS rock was already previously seen. So the weight of this is going to drop, and this weight is going to be higher because this is now unique. Similarly, when we get to here, SANS rock paper, SANS rock is in 2 documents, which means this number is going to be lower. Paper is, let me rephrase this, SANS rock is now in 3 documents, okay? Which means this value has now reduced further. Paper is going to be a slightly higher than SANS and rock, but scissors is unique. Why is this important? If you think about it, if your organization were to become compromised, it is more than likely that it is going to be a unique IP address that is going to be part of that compromise. I'm not saying that someone might not take advantage of a cloud environment that your organization goes to, but in general, it's going to be a unique IP address that is involved, or a unique domain, something that someone recently stood up. So what we want to ultimately do is add weights to these alerts, if you wish, and these different values. So we will say, let's say we do TF-IDF vect, right? And I will say TF-IDF vectorizer. I'm using the default values here. And I will say the vectorize, this is just a variable, right? Vectorize corpus is equal to TF-IDF vect, and I'm going to fit and transform on my corpus. Okay. Now, once everything is in place here, I'll set up a pandas data frame of the vectorized corpus, and we're going to take that and convert it to an array. And at the same time, we'll take the columns to be the TF-IDF vect get feature underscore names. Columns, C-O-L-U-M-N-S. Okay, so this is what I was talking about. Now we have the actual features, which is the similar text that is coming in from our alerts. And we say, in this example, we have SANS rock paper, SANS rock paper scissors. As you can see, in the first document, we have paper 0 and scissors 0. This is only because we have SANS and rock. And you can see this has a high value. But once we get to the second document, we can see SANS and rock have dropped, whilst paper has a higher value. And now that we got to the third document, we can see SANS rock has fallen even further, and scissors has the highest value, whereas paper, which is in 2 documents, has a value higher than SANS rock. Okay? So we're going to now take our alerts, our classified documents, and we are going to take this same concept and we are going to create our model. Now, the other problem is, in machine learning, you don't know which model is going to solve your problem best. So let's say we create a list and call it models, right? We'll just put this here. And now let's select a couple of different algorithms. For this problem, let's go ahead and say we, from sklearn, that pipeline, right? Because we're going to set up a pipeline or a couple pipelines. Let's say we import pipeline. Let's say for model creation, we say from sklearn.naive base, for example. Let's import complement naive base. Let's say we do from sklearn, and we're taking different types of algorithms. sklearn.linear model will import logistic regression. And let's say we do from sklearn dot ensemble, let's import AdaBoost classifier. And since we're here, let's also bring in some libraries that are going to help us with our metrics. So let's say from sklearn dot metrics import dot. Thanks, Sarah. Thanks, Sarah. Much appreciated. Plot. Let's say we want to plot the confusion matrix as well as we will take the classification report. Okay. Now that we have those, let's go ahead and build a couple of pipelines so we can test. The first pipeline we're going to build, let's name it naive base pipeline. And in here, we'll just say pipeline. And our pipeline is going to consist of, let's say, let me just do it this way. You close up this space here. Okay, so our pipeline for the naive base pipeline is going to consist of what we call the TF-IDF, right? And this is taking advantage for us of TF-IDF vectorizer. Now, we can do this manually or independently, but realistically, we are better off putting together a pipeline so that everything can be done at the same time, rather than running the vectorizer, then running the actual algorithm to build a model. We'll do it all right here. So we'll then say, okay, sorry, this needs to be in brackets. We'll now say here, let's call this naive base classifier. And in here, we'll say we want to use complement naive base, right? We're going to keep it with the default values. And in the interest of time, let's just copy, paste. And what we will do, we will change here to LR to represent logistic regression. Here, we'll change to ADA to represent AdaBoost. And similarly, we will change here, rather than NB classifier, actually, I will call this LR classifier. I will call this Ada classifier. And here, the classifier that we're going to use, we'll call it logistic regression. And here, we will just call AdaBoost classifier. Okay, so we have just built those different pipelines. Now that we have them, let's go ahead and say models, the list that we created earlier. Let's say we want to append, and we want to append these different values here, or these different pipelines. So I'll say append U, and let's just copy here. We paste it twice. Let's hope in copying and pasting we don't make mistakes. So we have naive base, we have logistic regression, LR pipeline, and we have the Ada pipeline. Okay. Now we press enter. We have these values in the model. We can confirm that by just simply typing models, and we would see that we have the different models inside, or different pipelines inside of our list. Okay. Let's now go ahead and actually build something with these, or do something with these models. So we can say for, let's pull this up here, for model in models, right? What we want to do first, let's do model.fit. And we are going to fit, and when we say fit, we're training the model. We'll say xtrain, we'll say this as type, we'll convert this to string. And because this is supervised machine learning, what do we need to do? We need to also provide the labels. So we'll say ytrain. Okay. We press enter. Actually, before we do, let's do something else. Let's say we get the model accuracy. Let's say print, and we'll do a format string. And we will say the model, right, accuracy is, and let's say we add here model.score, and we're going to score it against the test set versus the Y test. Okay. Let's go ahead and run this here now. Okay, what did we miss? Empty vocabulary. What did we miss? Xtrain. Let me see. Model for model in models. Extrain type string fit. Did we miss something? It says maybe the model contain only stop words. All right, you know what? I can come back and I can figure out what's going on here, but in the interest of time, let's just do this. We might have made a mistake somewhere when we were cleaning the data, but that's not a major problem. Let's find where we split the data and we'll use that data directly. Sorry, let me just go back up here. Okay, so we split it here, right? Let's just go back straight down. Let's ignore everything else. I think you got the idea of what we done before. So here, let me remove this now. We should be able to take extrain, run it without any problem. Okay, here we go. So now we have, it is reporting that complement naive Bayes is 86%. It is saying that logistic regression is 90%, right? And we have one more to go, which is the other boost. So at this point in time, you're probably saying, these models are performing awesome, 86%, 90%. You might or might not be correct. So let's wait on the next one, and then we will actually make a prediction. Whilst that is running, okay, it's finished. So we have 89%, we have 90%, we have 86%. Awesome. Let's go ahead now and make an actual prediction. Because the logistic regression, right, is the one with the highest accuracy, I will use this instead. So we'll take the logistic regression pipeline, right, and we'll say we want to predict. We want to predict on the test data set as type string. And when we predict, at the same time, just show us the first 10 records. We don't want to see everything. Okay, let's see now. Whoa, so here we have our predictions. From here, we've seen all zeros. So it is reporting that for the first 10 records, everything represents a false positive, as in the security tool triggered the alert, but there was nothing really meaningful there. When we investigated it, it turned out to be a non-issue. So here it's reporting as a false positive. But is this really true? Let's actually compare this with the real values. Let's go back into the Y test, and let's say we take the first 10 records. And here we can see at least 2 records are classified as true positives from the real data set, right? From the real X test. So here we have everything that is classified as 0, which means everything is a false positive. And you might be saying, but we just got 90% here, right? What is the problem here? Well, it is 90% accuracy because it's doing a good job predicting the zeros, which is the false positives. What we wanted to predict is the true positives. And to help you understand this a little bit more, let's look at this from a different perspective by going back upwards. Remember, we started off with this here, right? And we said that this here represents 85% of the data. This represents 15%. So simply selecting 0 gives it an automatic 85% chance, or I can reward this. It has 85% chance of selecting 0 versus 15 for selecting 1. So it's easier to just put your hand in a bag with more blue marbles than red to pull out a blue marble, which is exactly what we have here. So one of the big concerns in machine learning, especially for us supervised learning as we are dealing with classification, specifically binary classification problem, is we want to ensure that the data set is balanced. But if you're thinking about network intrusion and those type credit card fraud, the data set is more than likely never going to be balanced because there are more legitimate transactions than fraudulent ones. So for us, we have more false positive alerts than actual true alerts. So how do we address this? We have a couple of strategies we can use. We can truncate this data set here to match this one here so we have a balance. That would probably work. But guess what? You are now discarding about 70% of what might be valid data, right? That can help the learning process. So this is probably not the best solution. What we can do, maybe we can duplicate this here so that it has the same 85% as this over here. Obviously, it's not going to be 85-85, but more so 50-50 to round out 100%. But guess what? We did not introduce any new pattern here. We just duplicated the existing patterns. So that probably is not going to help. What we can do, we can take advantage of something called SMOTE, right? Synthetic minority oversampling techniques where we create synthetic versions of these so that we can balance out with this. Or we can assign class weights. We can say, okay, we'll put a class weight of, for this one that is 0, maybe we put a class weight of 1. And because we know maybe we had a ratio of 1 to 5, maybe we'll put this here. Where the 1 is, we'll give it a 5. So this gets a higher weight than this one. So this is why you don't want to always get caught up on accuracy as the metric you use for your machine learning problem. I promise we will wrap up soon, right? So with that said, let's go ahead and just look at it from 2 more perspectives in terms of visualizing how our model is performing. Because without the visualization, you are really going to lack the understanding of your model. Let's go ahead now. We already know the score. Let's go ahead and say, you know what? Let's go ahead and print the confusion matrix. This is an important tool when you're doing binary classification problems or even classification problems. So I'll say I want to print, and I will say confusion matrix for, and I'll just put model here, right? Just so that we understand what is going on. And for this, I am going to then create a new line, and I am going to use the plot confusion matrix. I'm going to give it the model, I'll give it the test data, and I'll give it the train data. Okay. Now, run this once again. You close off here. What did I miss? You close off here. Model, plot confusion matrix. Okay. Okay, I see where it is. White test. Okay, I think that's it. Now, when we print this here, we are going to get, come on. We are going to get our confusion matrix. And the confusion matrix is going to give us a much better visualization of what really is going on with our model. It is important that we are able to visualize our model's performance. We already know the accuracy, and we already know we should not rely on accuracy because, as we saw, it failed miserably here. So what we will take advantage of are 2 other things, the confusion matrix as well as the classification report. And then we will just create a final model. We'll use grid search, create a final model. We'll save that model, and we'll wrap up today. Okay? So just give me a couple more minutes, please. Thanks, Sarah. All right, so now we have the confusion matrix. Let's focus only on this one here because this is more than likely the one for logistic regression, but you get the idea here. What we have is, I think it's 8,000 plus records here. I think it's 8101 or something like that. We saw when we split the data set earlier. And here we have the true, let me keep coming. Here, these are true negatives, or let me rephrase this. When we classify the tickets or the alert trigger, we talk about it from the perspective of false positive or true positive. But when we build a classification report, you have, or build a confusion matrix here, you have to be a little bit more careful. This here represents true negative, non-issues. So we had over 6,000 tickets that were basically non-issues. At the same time, we had 753 tickets that were true positives. These were cause for concern. These are things that represent actual attacks that were seen in the environment. 278 here are classified as false positives from the confusion matrix perspective, and 493 are false negative. This here, for the problem we are trying to solve, is one of the biggest concern, because a false negative is a situation whereby your organization is compromised, but you don't know that it is compromised. So the threat is in your environment and you don't know. So from this model perspective, we want to reduce this false negative as much as possible from the model. But you also need to keep in mind that you are going to have a trade-off. The more you reduce this number, it is likely the higher this number is going to go. So you have to find that balance. Okay. Now, another thing you will hear about in machine learning is precision and recall versus the accuracy, for example, that we looked at. So here we're talking about precision. How precise was the model in terms of its predictions? Let me bring up my calculator for this one here. So if we bring up the calculator here, right? Bring up the calculator here. Come on. So here we have the calculator, right? We have, we're using this one here, okay? This entire confusion matrix. So we have 753 plus 278, right? So that's 1,300 records, 1,301, or 1,031, sorry. Out of this 1,031, how many did we get correct? So if we say 753 divided by 1031, we see we have about 73% precision, right? We have about 73% precision, which means we're doing very good here to some extent. And the next thing you might hear about is the recall from the actual true positives. How many did we get correct? So if we add 753 plus 493, we get 1246. And if we say 753 divided by 1246, we have only 60% recall. Might not be good. For us and the problem we're trying to solve, we should probably have a higher recall, because remember, the security tool is already reporting a lot of alerts. What we want to do is we want to figure out which ones are more meaningful. So if that means we have to accept some more false positives, that is fine. But we don't want to miss false negatives, right? So we need to optimize to ensure that this value here is as low as possible. Let's go ahead now and just do, we can look at the classification report, but in the interest of time, okay, let me just print the classification report just so that you get an idea what is going on here. So I would say, let's say print, and I will just remove these here. Let's remove the construction here so that we take less time. Let's say print classification report, right? Print the classification report. That should give us a better idea of what is going on. Okay. Now, we created the first model, or the first set of models, but we did not really optimize any parameters or anything like that. We just use the default values. In machine learning, you seldom are going to ever want to use the default values. So you ultimately have to find the correct hyperparameters to use. So whilst we're waiting on the classification report, let's go ahead and set up our logistic regression parameters, right? And we'll say we want to adjust parameters for the TF-IDF, right? We want to learn parameters, I should say, for TF-IDF, and this is the term frequency, inverse document frequency, that we defined as part of our pipeline earlier. And note the double underscore when we want to take advantage of a particular hyperparameter. In this case, we're going to decide between the n-gram range, right? And the values that we want to test, the values that we want to test are going to be in a list. And the values we will test specifically, we'll test 1 and 1, which is basically unigrams, or we'll test also for bigrams. Okay, and let's test max features. I'm going to skip some things in the interest of time. Okay, max df. No, let's say max features. And do we use 300? Is that the best number of features, or is it 500 for this model, or is it none? Okay, and similarly, let's add for the logistic regression part of the pipeline, let's say LR classifier, we'll say we want to add penalty, right? Because remember, we have an imbalanced data set. So let's say we decide on a penalty, but which penalty do we choose? I'm not sure. So I will tell the model, you know what, I need you to test with both L1 as well as L2 and none. And finally, let's do one more. Let's say, remember we spoke about balancing out the data set and we spoke about the class weights. Let's look at the class weights here, right? I'll say class underscore weights. And here, the weights that I wanted to test, are going to be for, or this is going to be in a dictionary. We'll say for 0, we want to test with 1, when 1 is 1. Similarly, and I will copy this here now. Right? I'll change this one to 3, and I'll change this one to 2. So now that we've set up our hyperparameter space, parameters. Okay, comma. Okay, now that we've set up our hyperparameter space, let's go ahead and take advantage of a tool that is going to allow us to efficiently search that space. And for that, we will say from sklearn.model selection import randomized search cross-validation. We can use grid search, but it's recommended to use random search because of the fact that you don't need to search the entire space. Just finding some good random values should be helpful. And let's set up now our cross-validation. Let's say LR randomize CV, right? We call randomized search cross-validation. We say we want to set up the estimator is our logistic regression pipeline, right? The parameter distribution that we want to use represents the parameters that we just created above there, right? The same parameters we just created. We say the scoring, rather than accuracy, we will use recall. The number of iterations we want to do this for is going to be equal to 5, right? Just for in the interest of time. And we are going to use cross-validation of 5, a 5-4 cross-validation, okay? And I'll just set a random state just to make this predictable. We'll call this 10. Let me go ahead and wrap here again so you can see, right? And once we have that, we will need to fit on our data. So we say randomize CV. Thanks, Sarah. Like how you're paying attention. My apologies, everyone. I know we're a little bit over, but we're going to wrap this up shortly. So we want to fit on the training type, the training set, right, as type, and we're going to use this as string. And remember, we need to use the test, the labels, which is going to be ytrain, right, because this is a supervised learning problem. So if we did everything correctly, we press enter, we see we have an error here. Why do we have an error? Let's figure out that. Invalid parameter, max features. Okay, so let's go back up here. Let's see. TF-IDF max features. You know what? Let me just remove this here rather than trying to diagnose this right now. Right. Okay, what did we miss here now? So this is what happens, as I said, class weights for logistic regression. Why is that a problem? Okay, let me just class logistic regression or class weight. Class weight. Run this again. Boom, let's get this right now. All right. So once we run this here now, we would be able to find, based on this search space that we specified, the best possible parameters for this problem. And do note, I use a very limited space, but the idea is you would ultimately go ahead and have a larger space. This is going to be dependent on your compute and all of these different things. This here should wrap up in another 5 seconds or so on. Let's see how it goes. But then from here, we will extract the best parameters. And let me come up here and take this pipeline again. We'll take this logistic regression pipeline. All right, let's take this one here. This is running. We'll take the logistic regression pipeline, and we will ultimately insert the values in here that are returned from this cross-validation. Take a little longer than I expected. Okay. All right, so now we have estimator failed to score on the training test set. Okay, let's give it a second. Something to do with a particular solver. Okay, what happens sometimes also is that some of the parameters might not match together. So this is why you might get errors. So it's not always a case whereby a particular hyperparameter is going to match with a different one. So for example, I might have specified L1 or L2 here, but it might not have matched with something else, maybe whatever is the default solver that is being used. Okay. All right, whilst we wait on this, let's go ahead. I have the values here, but let's go ahead and say that for the TF-IDF vectorizer, let's say we have n-gram range. Hold for me for a second, please. Hold for me for a second, please. Yeah, sorry about that, everyone. So yeah, so that is still running. It's running a little longer than I anticipated, but let's go ahead and let's say, for example, n-gram range was returned. And let's say it returned 1, 2, right, as the best possible parameters. Let's say for the max features, somehow it told us that max features 300 represents the best representation for this data set. And we can also add things such as max DF, minimum DF, and so on, right? So I'll say max DF 0.25, meaning that if something is seen within about 25% of the document, just ignore it. Similarly, for here, okay, so this is finished. So once it's finished now, we see here the parameters that it returns, right? So we can go ahead and we can ask it for the best parameters. We can say LR, we can say random CV. What are the best parameters that you got, right? And it says for the n-gram range, the best one is 1, 2. For the penalty, for logistic regression, we're better off using L2. So let's do that. Let's say penalty equal to L2. And it says the best class weight to use, let's copy this here, is this one here. So we'll copy and paste here and reuse these values, okay? Now, if everything went according to plan there, we now go ahead like we've done before, and we say LR pipeline. And we want to fit using this new data. We say xtrain, and we could have copied from above, okay? Xtrain.as type. And this type is string. And because once again, we are dealing with a supervised learning problem, we have to specify the labels. Okay, we run this here. We're fitting, and everything goes according to plan. We can then go ahead and test. Let's go ahead and write that up in the meantime. We say LR pipeline dot score, right? What is the score now? We give it the X test as well as the Y test. We have 89% accuracy. Let's go ahead and plot our confusion matrix just like we did before. Let's say plot. And we're preparing to wrap up here, okay? Plot confusion matrix. We say we want to give it the model, which is the LR pipeline. We want to give it the test data, right? X test. And we want to give it the Y test. So with our new hyperparameters, what does our confusion matrix look like? In this case, it looks like we increased, right? It looks like we increased the false negative, reduced the false positive, but this is not what we want. Let me do one more test here. Let's say we change this value from 1 to, let's say 3. See if it makes a difference. 1 to 3. Let's see if it makes a difference. We are fitting again on the data set. We are getting the score again, 87% now. Let's see here. Plot the confusion matrix. Okay, now we drop to 208. We want this number to be as small as possible, so you will have to continue optimizing your hyperparameters. 796, I'm cool with this because in this case, we have less false positive than we have true positives. Now, if you think about this here, right? Let me just print the classification report. Let's say print classification report. Let's say Y test. We give it the pipeline. Right, we want to predict on the pipeline. We want to predict on X test. Right? If you think about this here, we have, in this case, over 1,246 alerts that are being reported as true positives. Okay? If your organization has analysts and they're spending 1,246, if they have to analyze 1,246 alerts, and each one of those alerts takes 1 hour, for example, right? If you divide this by 24, you are taking, sorry, if we have with 1,256, sorry, let me get back here now. 1,256 plus 6,855, okay? You have over 8,000 alerts that your analysts have to analyze. And let's say each one takes 60 minutes, which is an hour, just doing this for round numbers, okay? it would take you, let's say we divide this by 24, it would take you 337 days to analyze these here. If we are able to just simply bring this down, let me divide this by 2, by less than 50%, you can see now we have 168 days. So from a business perspective, we have significantly have an impact here already because one, we have more meaningful alerts to analyze. The false positives are actually, we can probably pay less attention to these, but we need to be worried about the false negative that we're missing. But we can't accept the false positives here because these two together is not a major concern for us. We can analyze these here while saving significant time rather than analyzing every single thing. So this is just yet another tool to help us. And here, notice that our precision is 57 and our recall is 83, right? We would have loved to have the precision a little higher, but the recall is what matters most for us because we're dealing with an anomaly problem, a fraud problem, if you wish, something that is more, that is unlikely to give us a balanced data set. Okay. Now with this in place, we can wrap up the day. We can say, okay, now that we've built this model, we have one that is ready for production. Let's just go import pickle, right? And let's go ahead and pickle our model. Say pickle.dump. And now that we dump, we'll say, we'll give it, let's say the model that we want to dump. We'll say, in this case, I'll say open the file that we want to create it as. We'll say this file is named SANS model.pickle. And we will ultimately write this as a binary file. We save this, and this model is now saved on my file system. If I were to say dir sans model.pickle, we should see it here. Okay, we just saved that model on our file system. And finally, now that we need to use this model as part of our application, we can do import model, right? This is just a variable I'm creating, imported model, and I'm going to assign that to this same file. Okay. But I will say in this instance, pickle.load. Okay, and when it loads, I want to not create a new file, but I want to read an existing file. So now that I have this here, I have imported my model. In my application, I can now just go imported model.predict, and I can predict on my any new data that I have, and ultimately I will get the results that the model is providing. Okay. This was a much longer session than I anticipated, everyone. I really thought I could have gotten this done in 1 hour. But the takeaway for us here is that Dave typically used this opportunity to speak a lot about machine learning. So I wanted to continue along the same path so that you might be able to continue benefiting from Dave in this way. So if you want to learn more about machine learning from the cybersecurity professional perspective, SANS has the SEC 595. Where you can learn applied data science for machine learning. Tons of great material in that class. If you're interested in intrusion detection and understanding how we can use machine learning from the perspective of packets and so on, come hang out with us at the SEC 503 class. But once again, the big takeaway here for us today is that we wanted to see how we can use machine learning to help address the alert fatigue. All of our security tools are generating alerts. Which one of these alerts are really meaningful? When the tool generates the alert, the tool thinks that it is meaningful, but to us, it is not always that case. Okay. Question. I'm working on the same project, active learning approach, as you are. I was hoping if you could share that CSV file. No, I will not be sharing the CSV file. I'm sorry about that. I probably will put a copy of the notebook up on my GitHub page, but I will not be sharing the CSV file. I tried as much as possible to sanitize that data, but I don't want to take chances with that data. All right. Hey, everyone. Thanks for hanging out with me. I really appreciate you guys hanging around, you guys and gals hanging around. I know we went over, but hey, hopefully this session was beneficial and you found it really meaningful, and you can now go use this to see how you can leverage machine learning within your infrastructure, whether it's packets or logs or anything else, how you can leverage machine learning in your infrastructure. In this case, I was fortunate because I already had the classified data. But if that data was not classified, then maybe I needed to take advantage of an unsupervised learning problem. But for us, we were dealing with a supervised learning problem. Okay. All right, everyone. I don't want to keep you all back any longer. It's Friday. We've already extended beyond the time. So thank you for hanging out with me. Hope you enjoyed the session. I'm very grateful for the time you spent with me. Stay safe.